Hello, I am Emma Bohannon, and this will be my short lecture over synthetic aperture radar, its theories and applications. So, synthetic aperture radar, or known as SAR, is a type of active microwave radar system capable of producing high-resolution images of the Earth's surface, regardless of weather conditions or illumination. Unlike optical sensors, SAR operates day and night and penetrates clouds, smoke, and light vegetation. This lecture is going to cover SAR theory and advantages, range and azimuth resolution, the imaging process, real-world applications, and available SAR data resources. So let's go over some SAR theory. Traditional real aperture radar has a limited azimuth resolution because resolution depends on the physical antenna length. SAR gets past this limitation by synthesizing a large antenna aperture using platform motion. As a radar platform, such as a satellite or aircraft, moves along its flight path, it transmits pulses and records echoes from the same target at multiple positions. These echoes are phase coherent, allowing signal processing to form a virtual antenna much larger than the physical one. So let's look at some of the theory that defines SAR. So a received SAR signal can be shown as S as a function of t and tau is equal to sigma times exponential of -j times 4 pi r of t all over lambda. Sigma is the target reflectivity, r of t is the time-varying slant range, and lambda is the radar wavelength. And we can also look at the range detection and range resolution of SAR. So slant range R is going to be calculated as R is equal to C times lambda of t over 2, where C is the speed of light. Delta of t. C delta of t over 2. And delta t is the round trip time delay. Using transmitted signal bandwidth B, range resolution is going to be, I forget which that one is. We'll call it sigma sub r is equal to c over 2 times b. And we can go ahead and mention some of the advantages of SAR are going to be that it's got a high spatial resolution independent of altitude. It can do imaging in any weather and day and night, and it's very sensitive to surface roughness and moisture and geometry, which gives it advantage over a real physical radar. So azimuth detection and azimuth resolution to compare back to a real physical radar, azimuth resolution for a real aperture radar is going to be sigma sub az is equal to r lambda over L, where L is the physical length of the antenna. For SAR, azimuth resolution is sigma sub az is equal to L over 2. So as you can see, resolution is independent of range. And this increase in performance for azimuth resolution is exploited by something called the Doppler frequency shift caused by the platform motion. As the radar moves, a target produces a Doppler frequency history that is processed using azimuth compression. So SAR imaging process, this is a very important part of actually getting and compiling the SAR data that one receives. So the SAR imaging process consists of several steps. 1. Data acquisition, transmitting pulses and recording echoes. That's essentially just your actual measurement that you're taking with the radar. 2. Range compression, applying matched filtering to improve range resolution. 3. Azimuth compression, focusing the Doppler history to sharpen azimuth resolution. And 4. Image formation, mapping focused signals into a 2D image. One commonly used algorithm is, as we talked about before, the range Doppler algorithm, which performs a fast Fourier transform in azimuth, range cell migration correction, and an inverse fast Fourier transform for image reconstruction. The final image pixel intensity represents the radar backscatter coefficient related to surface properties. Sorry. Oh, okay. Some resources that that have a lot of SAR data out there that's publicly available. This is sort of a list of those that can be used to help give people data to try and develop new image processing techniques or faster imaging processing techniques, as that's a very big area of research. And yeah, in conclusion, synthetic aperture radar uses coherent signal processing and platform motion to achieve high-resolution imaging. Its strong theoretical foundation, wave propagation, Doppler processing, and Fourier analysis enables powerful applications across science, engineering, and security. And that is the end of this lecture.